I want to talk about polar coordinates today, and I want to start off by talking about the usual Cartesian coordinates, except from a certain point of view that maybe we're not used to. In the plane, you could have graphs of things. You could make up a straight line and call it x equals 0, which we usually call the y-axis. Mark off one unit of distance to the right and draw another vertical line to get x equal 1, x equal 2, x equal -1, x equal -2. You could continue doing that as long as you wanted to, and also you could draw in straight lines between any of these lines that we've drawn. Likewise, you could make up a horizontal line and call it y equals 0, which is usually known as the x-axis, y equal 1, y equal 2, y equal -1, y equal -2, and so on and so forth. And drawing all of this stuff in on one picture, we get the usual Cartesian coordinate system. There's the x-axis, y equals 0, the y-axis, x equals 0, the point where they cross each other is the origin, and we describe where we're at in the plane by telling which one of these vertical lines we're on and which one of these horizontal lines we're on. So I want to do a little example here. I'm going to take a point in the first quadrant so that the terminal side of my angle is in the first quadrant. I'm going to make x equal 5 and y equal 3. R squared is x squared plus y squared, which is 25 plus 9, which works out to be 34. Tangent of theta is 3/5, 0.6. If I do the optimistic thing, I'll just say that r is principal square root of 34, and also that theta is arctan of 3/5. Because I'm in the first quadrant, everything is going to work out fine. If I want decimal approximations, r is about 5.83 units of distance. Theta is about 30.96 degrees. I have my calculator set in degree mode here. Now, I want to do a sanity check. Our point, you remember, is x equal 5, y equal 3. Even out of the first quadrant in your trigonometry class, you defined cosine theta to be x over r and sine of theta to be y over r. You always took the r to be positive, at least for a while. This means that x is r cosine theta and y is r sine theta. And because these were part of the definition of sine and cosine to start with, we'll say that these two formulas always have to be true. As a sanity check, x is supposed to be r times cosine theta. That would be 34 times cosine of theta, which I'm going to be literal about, right, is arctan of 3/5, and sine multiplied by the radius should give me the y-coordinate from this formula. So I'm going to calculate square root of 34 times the cosine of the inverse tan of 3/5, and I get 5 back, which is the x-coordinate, just like it's supposed to be. I'll say second enter to bring my calculate line back up, and I'll back up until I'm on the cosine, and I'll change that to sine. The square root of 34 times sine inverse tan of 3/5 is 3, just like it's supposed to be. These are the x and y coordinates of the point. We had converted it over into polar and then used our other formulas to convert the polar back into Cartesian, and we get what we started with, which is good. I want to think about whether the trig functions are positive or negative in various quadrants. In quadrant 1, they're all positive. In quadrant 2, the sine is positive, the cosine is negative, the tangent is negative. In quadrant number 3, the sine is negative and the cosine is negative, but the tangent, being sine over cosine, negative over negative, is positive. And in quadrant 4, the sine is negative, the cosine's positive, and the tangent, being the ratio of sine over cosine again, is negative over positive, which is negative. If you measure an angle and then you add 180 degrees to it, you've gone half of 360 degrees beyond the angle you started with. So you've gone exactly 1/2 of a circle beyond where you started at. The coordinates of these points are related to each other. Take the coordinates of this point, flip the sign on both of them, and you'll have the point on the circle down here. So theta plus 180 degrees, or theta minus 180 degrees for that matter, is literally going to form a diameter of the circle with the original angle you had. They are literally diametrically opposite to each other. Because the only change in the coordinates is a plus sign or a minus sign change, that means that the trig functions for this angle, which we know positive, negative, the trig functions for this angle are the same as the trig functions for that angle, except you may have to adjust some plus and minus signs. The reason that I bring this up is as follows. If you look at it, the graph of the inverse sine function looks like this, the graph of inverse cosine looks like this, and the graph of inverse tangent looks like this. The range of a function, you'll remember, is the collection of all function values you can get. So the range of the inverse sine is all of the y values from negative pi over 2 to positive pi over 2. The answers, the y coordinates that comes out of inverse cosine could be as small as 0 or as big as pi. The range of the inverse tan is almost the same as the range of the inverse sine, except you can't actually get pi over 2 or negative pi over 2. If you revert back to thinking about the unit circle, the angles between negative 90 degrees and positive 90, or negative pi over 2 to pi over 2 radians, that would be the right-hand part of the plane. If I'm trying to calculate an angle, and I know what the sine of the angle is, if the terminal side of the angle is in quadrants 1 or 4, I can just hit whatever number the sine is with the inverse sine and I'll have my angle. It's a different story here. The answers that can come out of inverse cosine can't be just any old angle. It has to be between 0 and 180 degrees, or 0 to pi radians. And the inverse tan is similar to the inverse sine in this regard, except I can't actually get 90 degrees or negative 90 degrees. This range business, it sometimes causes us trouble. So I'm going to think about the Cartesian point, x equals -3, y equals 4. When you square -3, you get 9. Square 4, you get 16. Add them up, 25. Presuming that there's no issue with anything, square root of 25 is 5. So we'll take the r to be 5. Tangent of theta is -4/3. Theta is inverse tangent of 4 over -3. The reason I've got 2 exclamation points here is that's wrong. The inverse tangent can only give you answers back that are in quadrant 1 or quadrant 4, and this is not like that. So this is wrong, actually. But if I pretend I don't know that it's wrong, I can go on and calculate. In degrees, theta being inverse tan of 4 over -3 is -53.13 some odd degrees, which is not right. If you start on the polar axis and go -50 degrees, you're going to be down here, not up there. If you go off and you do a sanity check like we did before, I'll let you do it on your calculator if you like. 5 times cosine inverse tan of 4 over -3 works out to be 3, and 5 times sine inverse tan of 4 over -3 works out to be -4. There's good news and there's bad news. The 3 and the 4 are sort of right, but they've got the wrong signs on them. X is -3, not +3. Y is 4, not -4. If you figure out where 3, -4 is, it's diametrically opposite the point that you actually want. So this theta that I've calculated is 180 degrees in error. I can add 180 degrees to this angle, or I could subtract 180 degrees. That would take me halfway around a circle and land me at where I actually want to be. So if I'm in quadrant 1 or quadrant 4, I'm good with theta equals inverse tan of y over x. There's no problem. If I'm in quadrant 2 or quadrant 3, that can't be right, but it's almost right. I can calculate what I would naively use and then add 180 degrees to it. Or if it was more convenient, subtract 180 degrees, and then things will work out all right. This is one way to fix this. This is kind of more reasonable than the other way. If we ignore all these difficulties and just say r is always square root of x squared plus y squared, and theta is always inverse tan of y over x, half the time that's going to give us the wrong answer. But on the other hand, we've seen that it's almost the right answer, except the plus or minus sign on the x and the y need to be reversed. Another way you could fix this problem is to say, I don't care about any of that inverse trig function stuff. Theta is always going to be inverse tan of y over x, the end. If you're in quadrant 2 or 3, instead of letting r be square root of x squared plus y squared, let r equal the negative of square root of x squared plus y squared. This is going to reverse the sign on the calculated x's and y's, and since they were already wrong by a sign, this will fix you up. The negative of the negative of a correct answer is the correct answer. We've already seen in our previous classes how to deal with y equals f of x on the calculator. More recently, we've talked about parametric equations as well. If, one more time, we go into the mode settings, I'm going to set my angles here back to radians because that's how all sensible people do. In Calc 1, when you used your calculator, it was all FUNC. More recently, PAR for parametric, but now we're going to have POL for polar coordinates. And I want to look at a few simple graphs and then talk about our final two calculus topics. Firstly, we all know that x squared plus y squared, x squared plus y squared equals 16 is a circle centered at the origin. Radius squared equals 16, so the radius is 4. In terms of r, though, remember, depending on how we're going to do this, sometimes we might take the r to be negative. So as a simple example, I want to draw the graph of r equal 4 with my calculator set in polar mode. And then also, I want to look at r equals negative 4. So I'm going to go into my y equals menu, and I'm going to set r equal to 4. I'll put it on the standard viewing window, which as usual doesn't look much like a circle because of the whole oblong problem. So we have a circle. I'm going to zoom out so I can draw it again. It starts on the positive x-axis and appears to go counterclockwise. What if I used the negative of that? What if I didn't say r equals 4, but r equals negative 4? I get a circle. I'm going counterclockwise, but I started on the negative x-axis instead of the positive x-axis. So things are as you think they should be. Oh, and about your window settings, in Cartesian, the things that were really important to us were x-min and x-max, y-min and y-max. In parametric, we had those along with t-min and t-max, also t-step. In polar, you've got a theta-min, a theta-max, and theta-step, which is how much it's going to increase theta between points that it's going to plot. Another example is y equals 4x squared, which if you convert to polar, y is r times sine theta, x is r cosine theta, so y equals 4 times x squared is r sine theta equals 4r squared cosine squared theta. Presuming that r isn't 0, I can divide it out and find out that sine of theta is the same thing as 4r cosine squared theta, which tells me that r is sine of theta divided by 4 cosine squared theta. I've already put this in my calculator here. I'll draw it on the standard viewing window. And it's kind of interesting. Early on, when theta was 0, r was 0, so that you were at the origin. As theta increased, The r increases, the x and the y's are all positive, but then because the bottom of the fraction is 0 in various places, it jumped over to the other side and drew the other half in kind of a discontinuous way. Let me zoom in so that it will draw that again. So you see, even something as simple as a parabola, when you're using polar coordinates, may have some rather odd features on the graph as described in polar. There's nothing wrong with the graph though. Polar graphs themselves can take on various interesting shapes. We just saw that we can get a parabola from what we're doing. R equals a constant is a circle centered at the origin, but I want to think about what kind of thing is R equal 4 times cosine theta. So I'll use my calculator. I'll put the graph on the standard viewing window. Looks kind of like an ellipse, but you remember we've got the elongated problem. It looks more like a circle now. Maybe it actually is a circle and maybe it isn't. We can't really tell from the picture. So I want to show how you convert this into rectangular XY Cartesian coordinates. The first thing that strikes me is in terms of polar coordinates, the left-hand side is very simple. It's just one of the coordinates. Look at the right-hand side and think about what we know about the connection between x and y and r and theta. I look at that right-hand side and I think it's too bad that there's not a factor of r in the right-hand side. So multiply both sides of the equation by r. On the left, it doesn't really make life any harder on me because we know things about r squared. Over on the right, I've got 4 times r times cosine theta. And r times cosine theta is the x-coordinate of the point that we're looking at. So that makes life much easier. Even better, r squared is easy to convert over into Cartesian. R squared is always x squared plus y squared, regardless of how I'm doing the angle or whether I took the r to be positive or negative. This is always true. My equation now reads x squared plus y squared equals 4x, which I can rearrange to this, which I can complete the square on, which I can turn into x minus 2 squared plus y squared equals 4. So it really is a circle. It's a circle with a center at x equal 2, y equals 0, and the radius was 2. Of course, on the other hand, there's a wide variety of graphs in polar that don't have any simple analog in Cartesian. For example, I want to look at r equals 5 times sine of 3 times theta. I've already put the function into my calculator, so I'll put it on the standard viewing window. And then, as usual, I'm going to correct for the screen dimensions. This kind of shape is usually called flower shape or petals or some other such name. It kind of looks like a flower that has several petals to it. And in our last applications, we're going to calculate the distance around some of these things and also the area contained within one of them. I want to look at r equals 3 over 5 minus 6 times sine theta. I'll put this on the standard viewing window. And it kind of looks like something we've seen before. This looks like a hyperbola, but if I do the zoom in thing, the center is not at the origin. It's been shifted downwards. It turns out if you do the same kind of calculation we did for the circle, that you can argue that this is in fact a hyperbola, but it's not a form y squared over a squared minus x squared over b squared equals 1. It's a form y minus c squared over a squared minus x squared over b squared equals 1. Actually, that should be plus, which you remember shifts the whole graph in the direction negative c in the vertical direction. I'll omit the argument for that though. And lastly, nope, our final topic is not arg. I just stabbed myself with a pen. Our final topic is arc length, area, and at no extra cost, slope of the tangent line in terms of polar coordinates. The premise is that we're going to look at some graph of type r equals f of theta, and we'd like to calculate lengths along that curve and also areas associated with it. Now, the x-coordinate is the r, which is f of theta in this case, times cosine theta. Y is r sine theta. So really, if you're looking at this situation, these are nothing but parametric equations for x and y in terms of r. We already know how to find arc length in parametric. Instead of writing t down, we write theta instead, but that's just changing the name of the parameter. That doesn't amount to anything. I have to put in the smallest and biggest theta values that are relevant to me. I've got to do some calculating here. I've got to calculate derivative of x with respect to theta. F depends on theta. Cosine theta depends on theta. So do the product rule and calculate dy d theta at the same time. We'll come back to this at the end to get our slopes of tangent lines. Now, this is nothing but algebra. When you have a difference of two quantities squared, it's the first one squared minus twice the first one times the second one, plus the second one squared. So both dx d theta squared and dy d theta squared are easy to write out, although they are kind of ugly looking. But we're going to add these things together. Firstly, a miracle happens. Minus 2f prime f cosine theta sine theta plus 2 times f prime f cosine theta sine theta. When I add these two formulas together, the middle terms cancel out. Even better, when I add these together, there's a factor of f prime at theta squared in each term. So factor it out, and we're happy to see what's left remaining. When I add these two terms together, factor out f of theta squared, and I get my sine squared plus cosine squared back again, which is 1. F is the r coordinate. F prime is dr d theta. F is the r coordinate. And again, notice it doesn't matter if r is positive or negative because we're squaring both of these terms anyway. The arc length is the integral from a to b with respect to theta now of the square root of the square of dr d theta plus the square of r. So this is not much more involved than the kind of things that we've already done. So going back to the problem we were looking at earlier, r equals 5 sine of 3 theta, I'd like to find the arc length around one petal. I want to pick one of these three chunks and calculate the distance around it. In view of what we just said, this is not very difficult. I've got to take r and square it. I've got to figure out what drd theta is, which is obviously going to be 15 cosine of 3 theta. I have to square that also, add the two things together, calculate the square root, and integrate with respect to theta from the beginning theta value to the ending one. So really, the only issue here is how do I get the beginning and ending values? I want to start at the origin, and I want to have theta, say, increase, and let it increase until I'm back at the origin again. If theta is 0, r is 5 times sine of 3 times 0, that would be 0. So my lower limit of integration, I'm going to be optimistic here, will be theta equals 0. What is the next value of theta that makes r equal 0? For the sine of something to be 0, the something has to be a whole number times pi. So the next positive number that I'm going to get that makes r equal to 0 is going to be theta equals pi over 3. If I graph this on my calculator, I'll need to adjust the t range. I'm optimistic that this is going to take me around one loop of this graph, and I always have to do a sanity check to make sure I got my limits right. So I'm going to go from 0 to pi over 3. The graph is r equals 5 sine of 3 theta. Put it on the standard viewing window. The standard viewing window goes from 0 to 2 pi. So I've got to go back in here and fix that. If I change my window so that the theta goes from 0 to pi over 3, that does give me one of these loops, one of these petals. So 0 and pi over 3 are going to be my limits of integration. My arc length is given by the indicated integral, and being lazy, also being pessimistic about the chances of doing this in closed form, we work out that the arc length is about 16.706 units of distance. If you think back to chapter 7, when we began this course, we were talking about areas. And the idea of areas was always based on the idea that we would take a region that we're interested in, chop it up into a whole bunch of smaller regions, each one of which looked like something that was easy to think about in Cartesian coordinates. That would be rectangles. Then we multiplied height by width, added up all the chunks, took the limit as the appropriate thing went to 0, turned it into an integral, and that was the big trick we started off with. Well, here, towards the end, we're going to have some graph, r equals f of theta. I'm going to start at some theta value a, end at some theta value b, and I want to think about, firstly, the distance traveled along, which we now know how to do. Also, I want to think about the area between the curve and the origin. Instead of rectangles, I have to use shapes that are nice with respect to r and theta. And if you remember from 1730, if I have a sector of a circle, something that looks like this, I've got a certain angle in the middle and a radius. The area of that sector worked out to be 1/2 times the square of the radius times the angle that goes with the sector. So we're going to carve this up in a way that's very similar to what we did back in Calc 1, also what we did at the start of Chapter 7, and we'll use similar ideas to get the result that we want. So for a given little sector, The area is 1/2 times the square of the radius that goes with the theta value times how much I change the theta, add them all up, take the limit as the delta thetas all go to 0, and this becomes the integral with respect to theta of 1/2 times the square of the radius in terms of theta, integrated from the smallest value of interest to the biggest value of interest. Now, as a sanity check, I want to do a problem that I know what the answer is. I'm going to do r equal a constant. Also, my theta is going to go 0 to 2 pi, so I'm looking at an entire circle centered at the origin of radius c. We know what its area is. It's pi times c squared. So 1/2 radius squared, 1/2 c squared, integrated with respect to theta from 0 to 2 pi. Antiderivative of a constant is the constant times the variable. And when the dust finally settles, you get pi times c squared, just like you ought to. If I'd got something else, that would have shown there's something wrong with the way I'm thinking about this. So returning to the problem we were looking at, we have figured out what the limits on the integral ought to be. They ought to be 0 and pi over 3. The radius as a function of theta is 5 times sine of 3 theta. So when I write down 1/2 times the square of r, I'm talking about 1/2 times the 5 squared is 25, sine squared of 3 theta. This is the integral we have to do. And strangely, the area integral is much easier than the arclength form was. So we'll pull out one of our trig identities that says sine squared of something is 1/2 times 1 minus cosine of twice that something. I've already gone ahead and pulled out the extra factor of 1/2. 1 minus cosine of 2 times 3 theta would be 6 theta. When you do the antiderivative, you get theta minus 1/6 sine of 6 times theta, evaluated between 0 and pi over 3. Write down the values that the antiderivative produce for 0 and pi over 3. Obviously, this entire term is 0, so I don't have to worry about it anymore. 6 times pi over 3 is 2 pi. Sine of 2 pi is 0, so this chunk is 0 also. The only thing that amounts to anything here is the pi over 3. So when the dust finally settles, the area of one petal is 25 times pi divided by 12 square units of area. Lastly, slope of tangent line problem. So we're ending where we started, sort of, in calculus. We've already mentioned that if I have r equals f of t as my graph, then the connection between polar and Cartesian coordinates basically turn it into just an ordinary parametric equation problem. dy dx is dy d theta over dx d theta. And just as when we were looking with arc length, if you use the product rule to figure out what those derivatives are, you actually have a formula for the slope of the tangent line that goes with a given theta value. Now, looking at it, that's pretty messy, but there's one circumstance under which it simplifies tremendously. If you happen to have a point on the graph and the point is the origin, that means that r would be 0. That means f of theta would be 0 for that particular theta value. And these last two terms on the top and bottom go away. Assuming that f prime theta at that spot isn't 0, you can cancel the f prime of theta out, and all that's going to be left is sine of theta over cosine theta. So if you're on one of these r equals f of theta graphs, and you pass through the origin, given a couple of fairly mild conditions, the dy dx is just going to be tangent of theta. So I want to look at an example of that. So I'm going to look at the graph r equals 15 times sine theta times cosine theta. Make sure that the calculator is in radian mode. I'll put this on the standard viewing window, which I may have to adjust. Now that looks pretty good. I will do the square thing though. Looking at it, it looks like there's quite a few ways that this thing can pass through the origin. I want to figure out when r can be 0, and I'm only looking at the thetas between 0 and 2 pi. Now, the only way a product can be 0 is when one of the factors is 0. 15 is a positive constant, so I don't have to worry about it. Sine of theta being 0, theta equals 0 would work. Theta equals pi would work. Theta equals 2 pi would work. So the sine being 0 is going to give me 3 possible interesting situations. We'll see if any of them are identical with any of the others as we go along. It could also be that cosine of theta was 0. Cosine of something is 0 only when the something is an odd multiple of pi over 2. In the interval from 0 to 2 pi, I'm going to get theta equals pi over 2, theta equals 3 pi over 2, and 5 pi over 2 is outside my interval from 0 to 2 pi. So potentially, at least, I've got 1, 2, 3, 4, 5 of these thetas to look at. I'm going to use my calculator to draw pictures in the same sort of way that we've drawn before, and then we'll use our formula that we figured out to calculate the slope of the tangent line. For each one of my theta values, I'm going to draw a graph based on what I get off my calculator by restricting the thetas to be near 0, for instance, or near pi over 2, or near pi, 3 pi over 2, and 2 pi. For theta between 0 and 2 pi, this will tell me everything that I want to know. Now, just as we did before, I have to tinker around with the window settings to get informative pictures, but near theta equals 0, the graph looks like this. I predict I'm going to have a horizontal tangent line. The slope should be 0. Here, the graph looks like this, close to pi over 2. It looks like I'm going to get a vertical tangent line. The derivative will be undefined there. Here, looks horizontal again, looks vertical again, looks horizontal again. And things go just as we figure. When theta is 0, the slope of the tangent line is tangent of 0, which is 0. Pi over 2, I don't get a function value for dy dx because tangent of pi over 2 is undefined. When theta is pi, I end up with a horizontal tangent line. When theta is 3 pi over 2, the tangent line is vertical. I don't get a slope of dy dx value. And when theta is 2 pi, tangent of 2 pi, I get a horizontal tangent line again, just as we ought to. This has been a short, but I hope reasonably complete discussion of polar coordinates, parametric equations, conic sections. There is one other topic we may talk about. I'm not sure if I'm going to do that or not. In any case, I hope everyone's having a good week, and I'll actually be seeing some of you in person in the not too distant future. Have a great day.